I'm still not sure, dude. I don't think it shared the Zoom screen.
Do this. There, right?
There we go.
Well-
Yeah, thank you.
It's interesting thing because I didn't, well, this is supposed to be a, well, first of all, such a pleasure to be here and thank you, Brian, for the invitation. I really get this sort of, I don't even refer this one as a like a presentation or anything. This is supposed to be, at least supposed to be a conversation just among me as a new joining faculty and, you know, all these you students down here. Maybe you guys can teach me something regarding, you know, what's really going on with this IED of the chapter as well. I'm really just developing the lab right now. I'm still sort of struggling in terms of, you know, giving a title to the lab. But what I've been really focused on is fluid mechanics and particular emphasis on the aspect of active flow control. All right, I'll give you a bit of insight on that. As a matter of fact, I didn't even prepare this slide as slide. I'm gonna refer to a lot of YouTube videos to just sort of give you an idea of what, you know, what I mean, or actually what people generally mean by active flow control. Okay, so let's just go ahead. This is a craft flying in the air. Well, I'm actually having this one, but I guess I don't think it will work here, but let me see if I can. What I'm gonna do is sharing the entire screen. All right, so I think that will work better. And what I'm gonna click on is this link. First, I'm not gonna worry about the things here. Oh, I'm sorry. This is my second movie, but I want to show you. I'm gonna show you how this beautiful animal can fly, right? You see how stable his head is. This to me is probably the most beautiful thing of how creatures like this can handle its body motion in the air. He's like really flying in such an unsteady environment. You have all this wind gusts flowing through his body, and you see how he's maneuvering his wing just to sort of stabilize his body. In the meanwhile, the most impressive thing to me is that you see how stable his mind and his head is, right? Can you even imagine that? Can we human beings can sort of design a flying vehicles like this Kershaw can fly? Really not at the moment. We can design airplanes that flies really, really well, but there are some limitations for that. And why is that? Because we've been focusing on the control of the vehicle itself. This thing down there, there's a lot of things going on. It's not only just trying to control his body. Well, of course, the ultimate objective is about controlling his body. But what that creature is really trying to do is not just to control his body, it's actually trying to control the flow over its wing and even over the body itself. And how does it know where, when, or where this gust is supposed to come and where is it supposed to come from? Got all the sensors over his wing, right? So he's able to manage to sort of use minimal amount of sensing technique to know when and where the gust is coming from. Sensing and actuation, that's two most important components when it comes to control. Now, I don't want to be offending, but you see how humans not design, robots. And we still have problems. We still have struggling to get our robots to walk. I want to say this is a tremendous amount of work that has been doing this. And that's trying to offend anyone. This is actually really, really beautiful work for how human beings are able to get to this stage of getting robots to walk. Right? But why is this thing challenged? You can't really tell the robots own physics. They have problems managing their body motion. You know, we can walk really, really well because we don't really have a model building our brain. What we know is we have experience about the physics of our own body. So I can sort of stand on one feet, just in the sitting. Meanwhile, I can balance myself. Right? That's really the inverted pendulum problem. And why? How do I actually stabilize that inverted pendulum? I have to know the physics first and apply my control law in my brain to balance my body. I can do that really quickly. That's how a crystal is
Build custom industrial machines in days.
Right? So how do we actually get to the stage of controlling the body,
Design your
controlling the
machine in
flight,
the simplest online
as controlling the flow? Okay. This is what I'm saying, from flight control to flow control. What you're looking at here is this F-22, exhibiting or performing this Cobra maneuver, right? It's almost like putting a horizontal flight, but all of a sudden, it's just gonna pull it up, making this Cobra maneuver to having this surging and pitching motion to extremely high angle of attack. That's a really, really aggressive maneuver for what an airplane can do. It's not just about the dynamics, it's also about the structural strength itself. But if you think about control of such a complicated system as F-22, things boils down to control of really just 6 components. X, Y, Z, the state vector. X is the entire state vector. X is really just the 6 component of the location X, Y, and Z. X, Y, Z in terms of velocity and the roll, yaw, and pitch. That's really just the 6 component you have to worry about. And knowing those six components, you can control your airplane really, really well, right? But how do we actually push the boundary to get that maneuver even more aggressive, or have this maneuver, or having our airplane fly like that crystal I just showed you? We got to consider this one. We got to go beyond just controlling whatever is inside the circle, going outside the circle, talking about the fluid flow stuff. Now, what's the difference between flight control and fluid flow control? Well, flight control, the state vector X, that's really 6 components. Flow control, you have to worry about X dot, Y dot, Z dot in every single fluid location, in every single fluid element. How many elements do you have? Well, that's infinite number of elements you have to worry about if you really want to control the flow. And how do you sense the flow? How do you control each element of the flow? How many motors or actuators or linkages do you have in your robot? Well, I would say that's a respected number for how impressive robots nowadays can do. Thousands maybe, if you're actually doing a flow control. These 2 big matrices, A and B, can easily go beyond 10 million or even 100 million, simply because we have an extremely complicated turbulent flow system that we're looking at. So by the end of the day, if you really want trying to advance this field, we've got a big plan out here. If we're really trying to advance this field, the major challenge is the issue of big data. You want this controller to sort of perform in real time. You can't have the controller to have some sort of a time delay because just the computer can't really catch up with speed, right? However, because of the fluid flow system is such a high dimensional system where the computer can't really catch up with the speed, then everything is really lying down to how big that system is, how to address that. Well, I kind of want to sort of go back to the traditional versions of flow control, what we call as a passive. And you guys probably seen this a lot. But now we're kind of moving on to the active, the idea of active flow control. All right. Passive control, you see like these vortex generators. I think this is probably a 777 wing whatsoever. But what does these vortex generators do? When you have a uniform stream or the flow over the wing, these things generate, well, streamwise vorticity. And that will help to suppress this flow separation. I'm gonna show you a movie later. And there's also an active control example here. People are using plasma to help suppress the flow separation. So with the active flow control on, you have forcing on, you have the flow to attach, right? This is the stall state. You don't want it. Your airplane or whatever your air vehicle, that's really a state of lost control. You don't want it to happen. It's almost like you're driving a car skidding on snow or ice, right? This is something you want to, this is like you're having your air vehicle gripping to the ground, right? You want that state, but you don't want the flow separation. So how do you move from here to here? And actually the fact is, moving from this stage to that stage is what the challenges really are nowadays. This is, again, another YouTube movie, and you guys probably seen this before. This guy put a bunch of vortex generators near the units, all right? And in this case, in this particular snapshot, what they do is they only have vortex generators in the upper half of the wing. And now the lower half of the wing, you just don't have those. So in this higher angle of attack flight, you see how the strips is getting really turbulent because of the flow separation, right? But see what's on the top, flows are really, just attached to the surface. That's a good flow behavior. That's something you want. This is again the passive flow control, but really you can see how well it works.
Step into a world of endless possibilities.
So it's increasing the angle of attack. So you see how this thing gets really turbulent right now, right? Because the flow has separated. But on top, we're still somewhat behaving okay, or particularly towards the earlier state. Now, I think this guy eventually is this state, right? I still see that what the strips near the tip still behaving somewhat and the strips near the state. And I think eventually this guy just put like what? For example, see how both this is right? All of the voltage in the units. Okay, that's the idea. And this is an example of really just a passive flow control. Next, this is really just a picture. This is 787 Dreamliner. You can probably tell. Anyone can tell me what this Corona-shaped jet engine, what is the purpose of that?
Reduce noise.
Sorry?
Reduce noise.
Exactly. Perfect. What's your name, please?
Trevor.
Trevor. Yeah, so that's precisely how it works, right? So if you sort of know a little bit about this fluid dynamics of a jet, when you have a jet, pulling out from whatever the jet engine, you have ring vortices that is kind of shape forming, right? And it's this big ring vortices that's forming and start to interact between, two successive vortex rings. You start to generate a lot of noises, jet engine noises, with very extremely high sound pressure level. And that's, that's really just vintage for people on the ground, right? So now introducing this corona shape probably just towards the exhaust part of the jet engine. This is really designed to reduce the jet noise. Now, the next question, I don't think anyone here can answer because I don't even know how to answer that. How do they choose to design how many certain edges or crowns they want to have across the engine, across that circumferential direction? Well, I would say, I don't know how they do it, but this is essentially what my research has been doing. I can tell you some sort of a jet flow instability behavior that's supposed to look like in order to, say, break down the vortex ring structures in the quickest way possible by leveraging the flow stability, instability, essentially. You want the vortex ring to form, but also when it's forming, you introduce some sort of a circumferential instability wave so that even by the time it forms, it already carries that circumferential or azimuthal direction wave structure. That thing get amplified while propagating downstream. And eventually this thing just kind of dissipated into streamwise forces. And that helps to mitigate the jet engine, right? So this is a tremendous amount of work put into this. How do they simulate? This probably have to go beyond just experiments because that analysis needs to be done in a computational sense. How do they simulate a flow in this high Reynolds number, maybe with temperature variation? And now they dump this flow data into some sort of data analysis tool. Now we're again looking in the matrix about maybe 10 million by 10 million. Pulled out the eigenvalues, pulled out the eigenvectors, and according to the eigenvector, they choose, hey, this is my fast optimal circumferential wave number I'm supposed to throw in when designing this engine. Okay, so I think that's pretty cool, and not a lot of people can actually do this computationally or even experimentally. But if you sort of having some idea about the background when they first aim to developing this, I think it's actually pretty phenomenal. Right now, the next one. This is actually a rotor. This guy is actually pretty creative. I think they probably just put a what's that called? That's a GoPro. Yeah, the GoPro camera on the probably at the root of a rotor craft. At the root of one blade of the rotor craft, right? So this thing essentially just kind of you look along one blade while it's rotating. All right. So let's take a look. Anybody know what dynamic pitching for a rotor craft is? We'll talk a little bit about that, but let's take a look at these.
Maker was engineered from the ground up
for
the Urban Traveler.
And
in
I
order
suggest
to
you just stare at the blade, not the background. You're gonna get dizzy. All right. So you see the thing is actually changing its angle of attack all the time while it's rotating. Right? It's pitching while it's rotating. And this pitching motion is synchronized with its own rotations. Why does it need to be do that? Why does it need to do that? Why does it have to worry about aiming for different angles of attack during different phase of the rotation? Most of you might have seen this. This is a typical example of how rotor craft or its own rotor blades works, right? So you have this advancing blade, right? So your helicopter is moving upwards, right, in this direction. So you have an advancing blade where this, the blades on the right flank is kind of moving towards, facing the stream, facing the coming stream, right? Now on the left flank, you have this retreating blade where your blade is going in the same direction of the coming through. coming flow, right? So you would probably say the flow, the relative speed of the flow to the advancing blade is much higher than this guy. As a matter of fact, if your helicopter, moving velocity is so high, you may even end up facing this reverse flow, right? Because this retrieving blade is not really going above the velocity of how flow, this coming stream across this region. Because in terms of this rotary speed, this has the lowest speed across this circumferential direction, right? So think about this. You end up having this spot where the flow is actually flowing from the trailing edge to leading edge. Well, that's a problem. Now, going back to that dynamic pitching scenario, when you have the advancing blade where you have a higher relative speed across your airfoil, so you may expect higher lift, right? And towards the retreating blade, this side is, of course, relative velocity slower. One way to do it is you increase the angle of attack down here, so that you will somewhat balance out, the lower relative velocity on the retreating side, right? That's how they end up just balancing out different lift from the advancing phase and the retreating phase. Otherwise, if you don't do that, you're just having higher lift down here and lower lift down here, so your helicopter just kind of roll over. That's why they're introducing this dynamic pitching, right? Yes. Well, this thing has been there for about 30, 40 years, but this is still going on. And this actually caused a lot of structural challenges to the design as well. That's why, believe it or not, helicopter design is just much more complicated than just regular fixed wing design. And there's just this operational envelope where this helicopter just can't go beyond a certain traffic speed because of that and the stall, right? Now, this is another movie. This is actually a work that I get involved with University of Campinas in Brazil. But what they do here is they having this plunging. There's no pitching, but it's really just this kind of plunging and heaving airfoil. And what they do is
My job is to make
they
college.
introduce a
easy,
periodic
just
forcing
luck on that.
near the leading edge. Yeah. See if they can zoom this thing a little bit. So it's using the pitching motion as a motivating example, right? And I will just be quiet and let you guys see this, because I think my colleague did an awesome job making this move. This is when the simulation starts, right? And this is the going through a plunging motion. You have separation vortices form. Now you have this big leading edge vortex. If you're interested in this, I think Dr. G is an expert in that. Now it starts to accumulate vorticity. You have this low pressure core start to form. This is when your flow separation gets the worst during this plunging and heaving phase, right? You also start to have this trailing edge vortex form. Right, now they are interested in introducing some sort of blowing suction actuation, right? And see how it's gonna work with the separator. Compare that to the baseline case without any actuation, any control. At this stage, they're able to reduce quite a bit for the drag while approximately keeping the lift or at about the same level. Now that's the heaving motion where you don't have that. You pretty much just have the attached flows with that. All right, I think I really want to show this. I think it's just because I think my colleague did an awesome job making the move. That's a lot of work actually. So that's that. This is another movie used to be carried out in another university. This is again using plasma actuation to control the turbulent vapor transition and also to suppress the flow separation. Well, a little bit. I don't think this one has the movie. It was right now. You see they start to. This is a separation state, right? Now they kind of having that actual plasma actuator on. This thing ended up just creating a magnet hydrodynamic force, so that it can just kind of pulling your flow towards the surface of the air, right? Relieving that, the flow gets separated again, and just have the separation region becomes fully turbulent. All right. Okay. For some reason, I get this movie is really nicely created. Let me jump out and let me just play that movie outside. Okay, let's see. I'm gonna play this movie. This is actually one of my former colleagues. So this is again another turbulent flow simulation for a so-called cavity flow. I think here at MAE, Dr. Groland is doing some experiments about these, having a wall, opening up. But this is, of course, a purely large eddy simulation. And just, just a bit of background. This flow will, because of this, there's this feedback loop between the hydrodynamic instability and the acoustic wave impinging on the apple. So while it's impinging on the apple, we end up having acoustic wave traveling upstream and somehow forming a feedback loop to keep exciting the hydrodynamic instability. That's why in the baseline case, you see this very strong span-wise vortices rolling up and just impinge on the apple, creating a huge amount of pressure fluctuation. Well, that's not cool because that's going to causing damage to the structure of the cavity cell. Sometimes you even have what we call a store, right? Think about, in some sense, you have an inverted cavity. I'm not going to talk more about it, but anyway, that's kind of causing a lot of damage to the store and even the structure. What they do here is they introduce some sort of span-wise blowing, right? They can suppress that big span-wise rolling up structure. With that, they can reduce the pressure fluctuations at the apple. That's one great example of how active flow control works. Now, the other one is actually one of my earlier work too. Okay, this is getting crazy. All right, let's see another work. Oh, is it playing? Started with the same initial condition, and you start with the two-dimensional control, where this is actually sort of mimicking a plasma actuator, but this one is just a strip along the span-wise direction. The other one we call it 3D because it's some span-wise wavy structure, and you see how the 2D control gradually linearize the flow, and 3D structure, 3D control can suppress the one pound shedding, and in turn to sort of suppress the separation and reduce the drag, right? So these are actually little example of how flow control studies has been going on. So what is really challenging about that work is that it's not about how to get it work. It's about, hey, again, there's a huge parameter space we have to choose. what is the actuation frequency, temporal frequency, and what is the span-wise wave number in term for optimal suppression for the flow field for the separated flow. That's something we have to figure out, right? Okay, now say if we can go back to the slide. Okay. Okay. All right, so this might be a bit dry here, but I just want to emphasize again. Flow control is cool, but the major challenge lies in the high dimensionality. Again, infinite numbers of points you have to control. And Navier-Stokes equation by itself, it's lucky that we know the fluid flow is governed by the Navier-Stokes equation. In many other examples, dynamical systems doesn't always count with a governing equation that we derive, right? So how do we address that? That's another big point about how we control chaotic system even without any governing equation. A strong nonlinearity is precisely the case for fluid dynamics. Huge space of choice for placement of sensors and actuations. Hey, it's not just about putting in a rotor, a motor, or a sensor, and connecting linkage for a robot. We have a huge flow field, right? We probably want to place a sensor and actuator on the body of the vehicle to weigh. Again, that's a huge space to search. And control parameter space. Again, frequency, wave number, hold a lot. How do we leverage advanced analytical tools to get us answer like that? To design, again, that Corona shape of that 787 Dreamliner engine, right? That's a question we've been trying to address. But without all of these, we are trying to reduce the complexity of the fluid flow system. We seek modes. Remember that jet engine, the Dreamliner jet engine? Well, that's a circumferential mode. That's a circumferential mode if you actually get it excited, it is optimal in terms of suppressing the noise generation. But you want to seek for that low dimensional space. You want to find a good coordinate to describe the dynamics. You have modes for, this sinusoidal signal, Fourier modes, right? This black signal essentially only have two frequency components. You can describe this black signal with thousands or tens of thousands of time sequence data. But on frequency space, how many do you need? 4. 2 amplitudes, 2 frequencies. You get to construct that, right? Solid mechanics, you know how things vibrate. That's a mode. This is something we've been emphasizing. Fluid mechanics. You can also find modes for fluid mechanics. And all other multi-physics. Actually, this fluid structure interaction is a phenomenal one, right? I believe this is the on a bridge in Tacoma near that Seattle area. So, eventually you have like two instabilities between the fluid and the structures to start to interact with each other. Resonate causes this thing to just clash, right? That's not cool. But you wanted to find a low dimensional space to describe your dynamics. Frequency, again, and frequency and amplitude, that might be one thing comes first to your mind. Reduction of the solution space, you can have all of these mathematical tools for that. But most importantly, what you're really trying to do is to find the so-called coherent structure in your turbulence. Turbulence by itself is chaotic. It's not so chaotic because of its existence of coherent structure. It is something, it's a pattern that behaves in both space and time. We're going to summarize these sort of techniques in the next slide. But if we end up having a million by million dynamical systems of the fluid flow motion, while mapping it to this basis or to this coordinate defined for this coherent structures, we may just need to describe the dynamical system with only three factors. That's a huge amount of reduction in space. Now that you can implement for your, say your feedback control law to do real-time control. That's how flow control technology, if you want to advance that, this is a major challenge we want to address. Okay, one of the things I think very useful from a data science point of view is called kind of take that label sort of peering downward. Let me just let me just do this. It's called a proper orthogonal decomposition. Anybody hear this? No. How about the latter one? Principal component analysis. Anyone has a little bit of the biology background? This is something people from biology doing it. Principal component analysis. But what they really do, what these things really do, is to find the spatial oscillating pattern in your flow field. You have a flow over cylinder, you can take snapshots of the flow field, taking thousands of them, and you find how oscillations appearing in space are correlated with each other. So you can find the oscillation, you can even rank the energy of the oscillation in its mode, in terms of the rank of the mode. So you find for the first pair, you have almost about 94% of the energy, mode pair 2, mode pair 3, and mode pair 4. Eventually just gradually going down in terms of frequency, structure, but this is the spatially correlated structure or the pattern that you're trying to find. This might be still big. Let me give you another example about how things in Netflix or Amazon works. And this is essentially absolutely the same as you have to find that flow field correlation pattern or coherent pattern, right? Let's just say Netflix is keep collecting your data, collecting the data of its subscribers, right? So you have some subscriber 1, subscriber 2, all the way to a million or tens of millions of subscribers. So one day, I don't have a subscription, but I assume when you go onto Netflix, you watch a movie and it probably ask you to just click you like or you dislike that, right? So you may have subscriber 1 that's kind of watching through thousands of, well, probably not thousands of movies, but for all the movies he watched, he may check, hey, he likes this, he likes this one, but he doesn't like that one. Same for subscriber 2, subscriber 3. And what this principal component analysis has been doing is to find all these vectors, find the patterns across all these user data in terms of each individual vector, find the pattern among all of them. And just say, hey, I may be a big fan of, I don't know, say superhero movies. So if I watch Marvel movies from whatsoever, I may be, have a tendency to also like DC movies as well. That's the idea. And let's just say you like romance, you probably have some tendency to like drama as well. Hey, that's the pattern. So when people keep checking what they like and what they dislike, this pattern gets to form stronger and stronger, right? They can pull down this pattern through this thing called singular value decomposition. I'm not trying to throw out the equation for you, but this is essentially how it works. You form a data matrix A, you type in MATLAB SVD of A. You get that when you pull out this U, that's giving you an answer. What is the most strong pattern among this data? And if that, again, to be an Amazon user sort of data, and this is like product 1, product 2, all the way to product N, and you can also find what people are likely to buy if they already buy something in their history, right? So this is essentially how all of these data science has been really coming into play with addressing challenges in flow control and as well as the flow mechanics. That's one. The other one I kind of like is the only reason, I guess the reason I'm kind of want to introduce data science, well, maybe with a bit of data science and a bit of network science is that I don't think there are a lot of engineering students get exposed to these two topics a lot, at least not in the Department of MAE. But you absolutely know how this works. You have among the individuals, you have, I don't know, like 10 people in this room right now. So if I ask this question, who are the cool kids in this room? How do I find that? How do I quantify who are the cool kids? Well, that analysis gives me that. So you can sort of, quantify the interaction between each one of you by putting a flag in terms of the interaction strength to your interaction, right? So according to the interaction, I can say, hey, I want to sum over all the outgoing interactions or outgoing influences from each of you. And that may be giving me a good insight on who may be the coolest kid in this classroom, right? That's actually the idea. I didn't put that. That's actually the idea of the so-called out degree of your network. You can form this work, you can describe this network really just in this so-called adjacency matrix, Aij, where each of the component, Ij, describe the influence from I to J. You sum over J, hey, that's your the total influence from one point, from one individual to all the others, right? So that's probably the one way to describe, to actually pin down the cool kids. There's one thing I think we also have to address is that for fluid flows, things are varying in time. Now, in this case, we are looking at the same sort of time evolving network on top and on the top and on the bottom, right? But the only difference is that if I'm asking the question, if I'm passing a memo to one guy among the six, but I hope this memo can be received by the most amount of individuals in this network, who should I pass it to, right? So all the links are the same across day 1 to day 3. But on top, I'm kind of see this message at A, because on day 1, this guy seems to be the coolest guy. He has the most outgoing edges, right? So it probably makes a lot of sense if I pass it there. But on day 3, there's only 4 out of 6 getting this memo. Instead of passing the message to A, if I were to pass a message to C, who has no connection on day 1 at all. But relying on its connection appearing on day 2 and the connection pattern on day 3, eventually on day 3, everybody got an answer. How do we address that? How do we actually formulate a nice mathematical description to find who are the coolest kid, considering the time evolution of the network dynamics as well? Well, there are tools for that. And these tools are precisely extremely useful for the analysis for fluid flows. And this is what I do. You have a time evolving 2-dimensional turbulence. So what I do is I can say, hey, I want to pull out the vertical element xi and vertical element xj, and putting some sort of interaction between 2 elements, right? And while it's evolving, while this flow is evolving in time, these interaction Aij may change from time to time. But through some nice, I would say beautiful mathematical formulation, you get a pulled out from over a certain time horizon, say day 1 to day 3 again. That's your vorticity field in this condition. You get to pull out the coolest kid in this flow field using 2 different ways to quantify the interaction. Are either the vortex core, which has the strongest vorticity strength, or in between the main vortex dipole, the opposite sign vortex field. Well, does that make sense? Well, it might do, because if you know a little about the shear flow, this is the region where you have the maximum amount of shear. That's where your flow is being most unstable. Okay, you may still picking up with a lot of the fluid mechanics background, but when I get to see this, I'm extremely excited because it tells me a lot about the knowledge that's aligning with my understanding of fluid mechanics. I know shear layers are unstable, so if I poke the flow at those regions, I approach those cool kids, occupying in between the vortex sphere, I should be able to modify the flow, modify the entire fluid dynamic network in the optimal sense. All right, I won't go into detail, but I think that's just to give you a flavor. Last slide. I think I'm here today to give you a bit of the flavor about we are engineers. We know things from an engineering perspective, but many tools we haven't really get used to. Network is probably one of the case. Data science well is emerging, but are we engineers able to sort of learn or customize this data science tools for the challenges that you're trying to address? Well, that's maybe the last message I want to convey. Not really to teach you anything, but maybe just to share a bit of my perspectives. All right, thank you very much. That's pretty much the I apologize again, I didn't make this too
How did you learn, like the data science side of it and the network side of it?
So let me see if we can do this. I guess, how do I learn? I'm not sure whether that's a fair question to ask of how do I learn. It's just the tool is out there, and I'm pretty sure many of you might get involved with the use of machine learning, right? Deep neural networks and all this stuff. I think this is the era where you at least need to hear about those terms at least. You may not be able to, code it up in Python or whatsoever, but it's almost like a common language among engineers or statisticians and all the stuff. But I think if I were to answer that question, I know that thing a little bit, and I know it will help me to address the need of my research. So you just have to get your hands, you just have to get your hands dirty in terms of learn a little bit about that. And I won't lie, these involves with a lot of linear algebra. And I did feel a little bit, quite a bit stretched when I'm getting involved with this. So I'm saying, as you train as an engineer, rather than a mathematician. But once you get through that, I think it's pretty much just a downhill for you to push yourself further. Yep. Questions, comments, interests?
Who else is doing this type of research, like around the country and around the globe?
I would say this is really big right now. I think, in my opinion, fluid mechanics is a fairly traditional field. So if you get involved with many labs, at least here at MAE, I don't think you get to see this kind of use for these, I won't even call it modern, these just tool sets a lot. But I think people are start to noticing the use of it. I've been working with quite a lot of the other faculty members here in the department, and they all show interest, and they're even pushing further for doing things within this using this tool sets because they just find it useful. if you were to ask what are the active institutes who's really on the frontier pushing the boundary for this field, if I were to name a few, University of Washington, Princeton, of course, Caltech. I got my PhD from Florida State. I think the research there with these tools were pretty active as well. I would just say, I think I would always encourage you to get exposed to some of these materials, getting you trained to know how to use them or to understand all the math. It's not my intention here. But if you were able to pick up a term like principal component analysis, singular value decomposition, proper orthogonal analysis, say 5 years down the road saying, hey, there was a crazy guy called Chion used to throw this term out to me. And I think this an hour that we just spent was simply just worth it, right? It's not my intention to go get you through, but I want you to know that there are tools out there that can be really generalizable to pretty much all the fields that you may be interested in.
I think on like the Boeing 787, they have like turbulence control where there's flaps on the wings that can decrease the turbulence. Is that the same kind of process that's going on here where they're trying to model with different things, or would that be a different way that they're going to accomplish this?
Yeah, that's an excellent question. Actually, I have a similar research project that has been going on. I don't know about what you precisely mean by turbulence, because turbulence by itself is probably of much smaller amplitude in terms of fluctuation. But if you're really talking about those big rolling up structure, the vortex shedding, and even the tip vortex, you always have like two vortices in opposite side, rolling up from the tip, right? So I think making those vortex pairs to dissipate soon is one of my interests. Then to answer your question, if it's talking about the stability of the vehicle, then that's not quite similar to what I'm trying to precisely address here. But there can be interactions between one turbulent structure and the other, and whether this interaction can be amplified in time or decaying in time, or how do we leverage this decaying or amplification mechanism to do flow control, then that's precisely what I'm trying to do.
Cool, thank you.
Cool. All right, so I'll just, I guess, sign off here.
Thank you for coming.
And